So the assignment for this week is intended to give you some more experience with writing functions in Visual Basic. And the problem that I want you to do is to determine the hydraulic head and the hydraulic head gradient in the vicinity of a well at steady state. And that function is the time solution, THEIM, and it's given here. So this is the hydraulic head, the pumping rate of the well, the transmissivity of the aquifer, and the radial distance from the well, and that's the radius of the well. So this gives the hydraulic head as a function of the radial distance from the well. And this is the regional head gradient, and this is the x-coordinate. Okay, so what we need to do to plot this up is we need some values, and so here are the values that you should use. And this this problem here is a new problem, and so you need to make sure that you have the latest version of the notes to find it. Let's see, it's on page 12 of the notes. So you're going to have to write a function for this equation, and in order to plot this, the plot that we'll make will be in Cartesian coordinates in x and y. And so this is a function of the radial coordinate, the radial distance from the well. And so what we need to do is transform the radial distance from the well into the xy coordinate system, into Cartesian coordinates. And the way that this is done is like this. You probably recognize this transform without the xw and yw. It's just this, in that case it would be square root of x squared plus y squared, which would be the hypotenuse of triangle. What we do is modify that by using x minus xw and y minus yw. That essentially translates this transformation to the location xw and yw. So that allows us to have the well located at any position that we want. That just makes the function a little more versatile. So here's what you should do. You need to write a Visual Basic function for this expression, and then plot it up over this interval, 0 to 180 of x and 0 to 180 in y. And along the way, you can try out your function by calculating it at this particular point, and the value is there. So it's given there in the notes. So you can verify, see if your solution is working well. And then once you can make a plot of the hydraulic head, contour plot, then I also want you to make a contour plot of the finite difference, or of the hydraulic head gradient, dH dx and dH dy, and make contour plots of that. So let me show you how to get started. Here are the parameters for this problem. So I wrote this out and highlighted it, and then went to create from selection and made the names. And if we check the name manager, we can see that we've defined these names. These are all names that are just given in the notes. Notice though that I don't use a variable name called Q. I call it flow. And one thing that would be good to do, just for clarity, is to put in the units here. So it's meters cubed per minute, meters squared per minute, and so on. So you should include that. Now we want to make a 2D plot. So the easiest way to do that is to just make a coordinate, x coordinate along the top row, and y coordinate along the first column. And so what I'm going to do is make my y-coordinate go from 0 to 180 in increments of 10. So start off at 0, and this cell is 10 plus that cell, and if I set it up like that, I can copy it down, and we have it incrementing automatically to give us this column. And what we can also do, let me just erase this, is similar thing along this row. So there's 0. This just equals 10 plus that cell, and then we can copy that, and if we copy it along the row, it gets incremented just like it does along a column. So at this point we have a function, and this is a function that I wrote in Visual Basic, and it's going to determine the head in 2 dimensions, x and y, and it has a variety of things that need to get passed into that function: the flow rate, the transmissivity, the radius of the well, x and y locations of the well, and the regional gradient. And if we do that, then it returns this value. What I've done is I say, okay, B1 is the x value and A2 is the y value. And what I've also done is I put this $sign on the row. So what happens then is when I copy it down, I go here, the row index is not advanced, and that allows this to function. If I didn't do that, then I would always use for the coordinate the point right above it, and that is not what I want to do. That would be a mistake. And so also I freeze with this $sign the row or the column of the y locations, and I do that right there. And so if I copy it over in this direction, we see that the column is not indexed, but in this case the row is indexed, or in I'm sorry, for the upper row, for the x value, if we copy it along the row, the column is indexed. So we started here with column B, and then we go here, it's column D. So in this case, I'm getting the x value here and the y value here. So it's quite a powerful way to have the coordinates automatically indexed. And what it allows me to do is write this function out like this, and write my x coordinates here, my y coordinates here, and then I can simply copy it down, and with all of that stuff highlighted, I copy it over to there. So those are the hydraulic heads every 10 meters in this region. Okay, so we need to plot this up, but before we do that, let's take a quick look over in Visual Basic. So here's what the header of this function looks like. I called it time plus regional, the time solution plus regional. And then I've got these parameters that I'm passing in, and I'm giving them variable types. These are all double precision variables. So there's x and y location and so on. And the last one is the regional gradient. And then when I finish calculating, I'm going to return a double precision number right there. So this is what I'm passing in, and internally I have 2 local variables that I use within this function. One is called a term, and that's just a term that I use. I think actually when I write it out, I think what I did was calculate that stuff, q over 2 pi t, as something that I call a term, just for convenience. And then also we need pi in this function, and so I have a variable called pi, and I'm going to calculate pi this way. This is just a simple way. It's a lot easier than writing out pi to many digits. It's just 4 times the arctangent of 1. So then my function goes here, and it's just a function that is these two equations. And I split it up so that I don't calculate everything at once, just for clarity. And so I have that function and I call it here and I get the result. So now we want to visualize this, and the way to do that is just to highlight the whole thing, including these coordinates. And then we can go to insert chart, and Excel will do some charts that are somewhat reasonable at doing a two-dimensional surface. Let's try this wireframe in 3D. So there's what this thing looks like, and you can see the well here. This is the hydraulic head being drawn down around the well. You can see the regional gradient sloping in that direction. And we might want to rotate this around to get a little bit better view of what's going on. And so let's see. So that might be helpful. Maybe rotate it this way. Okay. Rotate it back. Okay, so there's what the result looks like. It'll also do regular contour map, just in map view, and do that by going back to more or less the same place. This is a filled contour map, so there's what it looks like. And we might want to adjust the contours here. We don't really get very complete picture of the contour intervals, but those are the ways that we can show this kind of a field. In general, Excel is really not very good at displaying these kinds of surfaces. We'll use a program later on in the course that's much better suited to this, but this is convenient, and it's good enough at this point to be able to visualize what these surfaces are like. Okay, so I want you to plot this up and experiment around with the settings, and then I also want you to get the hydraulic head gradient. So what I did over here was to write a function called gradient that will calculate the hydraulic head gradient. And what I do is pass in 3 values. So B2, so basically I'm calculating the gradient at x equals 10, y equals 0, and this is the gradient in the x direction. So I'm using these 2 values, and I'm calculating the gradient here. So this is a centered difference, and in this case I just give it what delta x is. And so delta x is the distance between those 2 points. So I just give it 20. So the function it's pretty simple. It's just d2 minus b2 divided by whatever that variable name is in the function that I wrote. So there it is, and I can go and I should make this well, actually in this case this is drawing on the hydraulic heads over here. So if I just copy this down, as I've done already, then right here it's the gradient at that point is using those 2 heads. So the indexing is done correctly here, And we also see that we can't calculate what the gradient is here using this particular function. Actually, I guess that we could. No. Yeah, actually, we could, because this function is just taking that minus that divided by that. So we could we could we could use this function to write a forward difference at this column as well. So I've used this function to get dh dx, and I also have I just copied these x and y locations, copied them from over here. So this guy here is a plot of the gradient in the x direction, and we could go and do a similar thing over here for the gradient in the y direction, and I'd like you to do that. Okay, so that's really a quick rundown of the homework.